Hello, hello. Here's your problem set 7.2 video key. If you were in class when we did this, there's some stuff on here that we didn't necessarily discuss in class, so I'll go over that very quickly. Some of it I'm just going to have you read, like number one, what is a polynomial? A polynomial is a bunch of power functions added or subtracted, which, we've done quadratics, cubics. Those are all types of polynomials. The word rational is, in math at least, is something that can be written as a fraction, because we've talked about rational numbers. So we're going to take a rational function now, where we have a polynomial on top and a polynomial on bottom of a fraction. And then y must q of x not equal 0 in this definition up here, and that's because you're not allowed to divide by 0. So we're going to graph y equals 1 over x, and we know that x is not allowed to equal 0. And if x is not allowed to equal 0, then it creates two parts to the graph like this. Since x is not allowed to equal 0, this graph is not allowed to cross the y-axis because that's where x equals 0. And then we talked a little bit, again, why this graph goes up forever versus as why it flattens out forever over here. And that's all based on the fact that this is the graph of 1 over x. I'll write it real big here. And so when we make x a bigger and bigger value, like make x 10, 100, a million, it's 1/10, 1/100th, 1/1,000,000th. So as we go farther and farther out here, this value gets smaller and smaller and smaller. As your denominator of a number gets bigger and bigger and bigger, the overall value of your number gets smaller and smaller and smaller. And so, it's always, but it would never be 0 because the numerator isn't 0. That's the only way to get 0 in a fraction, is if the numerator is 0. Then the reason it goes up forever is kind of like the opposite of that. As x goes this way and gets closer to 0, that means your denominator is getting smaller and smaller and smaller. Well, a smaller and smaller and smaller denominator results in a bigger and bigger value of your number overall. For example, if we used, if we plug in 1/2, 1 over 1/2 is 2. If we plug in a number smaller than 1/2, like 1/10, 1 over 1/10 is 10. Or make it 1 over 100th, and you would get 100. So you can see as this value gets smaller and smaller, the overall value of your number gets bigger and bigger. And so that is why this side of the graph goes up forever. Over here, the same thing happens, except the numbers are negative. So all your y values are negative, so they become really big negative numbers. So it goes down to negative infinity. Okay? So this graph has a vertical asymptote at x equals 0 and a horizontal asymptote at y equals 0. Domain and range, you can just look at that here. These graphs are called hyperbolas, and we can talk about a, h, and k like we do with every other graph. This stretches it, which you don't really notice a whole lot. Like if this is the graph of 1 over x, 2 over x is going to look like this and just be like barely above it here, and same thing kind of like here, but they're going to look really close to each other. So more importantly would be when a is negative, it's going to flip the graph. So this piece would flip down here and it would look like that, and this other piece would be up here like that. So just make sure you pay attention to that. You can just read through this here. All right, so how do we graph this then? All I'm really interested in is where the vertical asymptote and the horizontal asymptotes are, and then I don't really need any specific points. We could find some, but we don't need them. So this shifts the graph left 3 units, or you could understand that the value that makes this equal 0 is -3, and you're not allowed to be 0 on the bottom, and that's what creates a vertical asymptote. So that's also a reason why it shifts left 3 as opposed to right 3. And then this makes the graph go down 1, which is illustrated here, and then you can just sketch a graph here and here. It's basically just moving the quadrants. Like this is kind of like a new x and y axis as opposed to this. And then you're going to have a piece in 2 of the different quadrants essentially. Okay. That is when there's no x up here. Then there's also rational functions where there is an x like this. You still get the vertical asymptote the same way, which is when the denominator is 0. So over here, I've just set this equal to 0 and solved it for x, and you get x equals -d over c. That's just a general way to write it. But just set your denominator equal to 0 and solve for x, and then those are the values. That's where we say, that's what x is not allowed to equal. But for the horizontal asymptote, this is where we talk about Bill Gates' philosophy. I'm just going to make up another expression over here. So if we had f of x equals 3x plus 7 over 6x minus 4. So remember, a horizontal asymptote is an end behavior of a graph. So we're talking about as x gets really big positive or really big negative, so infinity or negative infinity. So when you plug in like 1 for x, well, just looking at the top, we can make the same argument at the bottom. But if you just plug in 1 for x, you would get 10. If you plug in 2 for x, you would get 13. Well, the difference between 10 and 13 is fairly significant when you're talking about small numbers. But if you plug in 1,000,000 versus 1,000,001, well, if you plug in 1,000,000, you get 3,000,007. If you plug in 1,000,001, you get 3,000,010. They're still 3 apart, but when those numbers are that big, like, add $7 to Bill Gates' bank account, and it doesn't matter. So as x gets really big, this number becomes insignificant, and so does this number for the exact same reason. So the function simplifies to 3x over 6x, and when we think about it like that, well, then we can just cancel the x's and reduce 3 over 6 to get 1/2. So you would get a horizontal asymptote of 1/2 in that situation. Okay, so that's what's going on here with horizontal asymptotes, the Bill Gates philosophy. So coming down here, we built our vertical asymptote. So we're going to graph this one. Our vertical asymptote comes from the bottom equaling 0. So set this equal to 0 and solve. You get x equals 2, which I showed right here. Okay, and then remember, x equals 2 is what makes the bottom 0. So we're like, x is not allowed to be that number. And then for the horizontal asymptotes, we Bill Gates it. This number doesn't matter. This number doesn't matter. And you just have 1x over 2x, which simplifies to 1/2. Okay, plot those asymptotes with dashed lines, and then draw your curve. Okay, this one, start with the parent function. So since there's no x up here, it just goes right 2 and up 3. And so there you go. Okay, write a rational function that has a vertical asymptote of -4. Well, you need x plus 4 on the bottom, or like 2x plus 8, something like that. And a horizontal asymptote of y equals 3. You can just do this and do shifts. Now, what if you had to add an x on top? Because sometimes I put that stipulation in there. Well, the bottom can be the same. Like a vertical asymptote comes from that no matter what. And if the horizontal asymptote is 3, just put a 3x on top, or 3x plus any number. Because when you Bill Gates it, these numbers don't matter, and you just get 3x over x. The x's cancel, and you would just get 3. Okay. And then graph this one without a calculator. Once again, vertical asymptote comes from this being 0. So set this equal to 0 and solve. You get 1/2, which is why that's a vertical asymptote. Horizontal asymptote, we Bill Gates, so ignore, and you get -14x over 2x. The x's cancel, and you get -14 over 2, which is -7. So you have a horizontal asymptote there, and then you have a piece of the graph there and a piece of the graph there. And that's it.